Hello, everyone. So now, previously we have talked about permutation groups. We defined the definition and the notation. So at this time, we said that a permutation is a set of a set A is a function from A to A that is both one and onto. And if you collect all those permutations in a set, they will create a group under a function compositions. Okay, we define. So as a permutation is a function, so it's gonna be a mapping from once from the set and to itself. And there is another way of writing a permutation which is known as array notation. And the composition of permutations is done by in this way, like we do composition in functions. If you think about them, so first we do the So, like if you want to compose gamma and sigma, first you do the sigma, and then you take the the output, the image of the output of sigma inside the gamma, and that will be the output for the composition. And then we define the symmetric group. So let's say on first on three elements, and symmetric group contains all the permutations or the symmetries of a set of certain objects. And then we define the symmetric groups Sn. And then we talked about that if you collect the symmetries of a square, that's also the symmetric group, subgroup of a symmetric group and of S4. Now we will give another notation which is like quite simpler than the previous notations. We call it the cycle notation. And it was first given by the French mathematician Cauchy in 1850. And it has theoretical advantages in that certain important properties of permutations can be readily determined when cycle notation is used. So, so let's consider. So let alpha be a permutation. So alpha be a permutation which is 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 6, 5 goes to 5, and 6 goes to 3, right? Okay. Now, this assignment of values could be presented systematically as follows. So we say that let's have first we can have 1 here and 2 here, and then we say that there's a cycle going on from here to here and here to here, and this we call, this should be a looks, this should look like a circle, but trying is very bad. So this is alpha, this is alpha. Okay, so one sends alpha sends 1 to 2, and then alpha sends 2 to 1, and then we have 3 and 4, and then 6, and then we say this goes here, this goes here, and this goes here. So alpha send 3 to 4, alpha send 4 to 6, and alpha send 6 to 3. That's again a cycle. And then we have another one, which is which is this one, and this is again a cycle, but it is itself. It is on to itself. So alpha sends 5 to 5. Okay, and then although this is mathematically satisfactory, such diagrams are cumbersome. They are very hard and time taking. So instead, we leave out the arrows and simply write that we have 1, 2, and then we have 3, 4, 6. We separate them by comma, and then which is fixed, we just write it like this. Okay, and then we combine them. So alpha would be 1, 2, and we do not give the comma after the bracket. We just write them like this, right? Okay, and this is alpha, and we can present the second example, which says let beta be a permutation, which is which sends 1 to 5, 2 to 3, 3 to 1, 4 to 6, 5 to 2, and 6 to 4, right? Now in cycle notation, beta can be written as 2, 3, 1, 5, 6, 4, or it can be written 4, 6, 3, 1, 5, 2. Since both of these unambiguously specify the function beta. Now, an expression of the form an expression of the form, which form? The form which we have A1, A2 up to AM is called a cycle of length M or an M cycle. Okay. Now, multiplication of cycles can be introduced by thinking of a cycle as a permutation that fixes any symbol not appearing in the cycle. So thus, the cycle let's say the cycle where we have 4, 6 represents permutation where if 1, 2, 3, and 5 are not appearing, that means they are sent back to themselves. Now 4 is there, so 4 is going to 6, 5 is fixed again, and 6 goes to 4. Okay, and in this way we can multiply cycles by thinking of them as permutations given an array form. Now consider the following example from S8. So consider, let me write consider a following example from case 8. Okay, late alpha is a permutation which is 1 3 2 7 4 5 6 8. If I'm not giving commas, it means it's fine. They are there. And beta is 1 2 3 7 6 4 8 5. Now, when the domain consists of single digit integers, it is common practice to omit the commas between the digits. So, what is the cycle form of alpha beta? The question is that. Okay, what is the cycle form of alpha beta? Let's write alpha beta here. Okay, now, of course, one could say that alpha beta is nothing but just combine all of them. So that is 1 3 2 7 4 5 6 and 8, and then we have 1 2 3 7 6 4 8 and 5. Okay, now, but is it usually more desirable to express a permutation in a disjoint cycle form? It is. That is, the various cycles have no number in common. So we want to write them in a disjoint cycle forms, like the various cycles. The cycles have no number in common. That means, like, you can see 1 3 2 7 are appearing in the beta form. So we want to omit them and write only single digits. So, and well, keeping in mind that the function's composition is done from right to left, and each cycle that does not contain a symbol fixes the symbol. Okay, so we observe that 5 fixes in in here in here 5 fixes, right? Over here 5 is fixed, and so 5 fixes 1 actually. So let's start with 1. Sorry, 5 fixes 1. This cycle fixes 1. Then 6 4 8 fixes 1. Now 1 2 3 sends 1 to 2. That means we can write 1 here and see. Now 1 2 3 sends 1 to 2. Now we look at 8 fixes 2, 4 5 fixes 2, 2 7 sends 2 to 7. That means we can write 1 to 7. Right? And again, we 1 3 fixes 7. Now we are back at 5. Thus, we begin that alpha beta is equals to 1 7. Now we are back at 5. Now repeating the entire process, beginning with 7, we have cycle by cycle, right to the left. You see 7 goes to 1, and then in over here in 1 3, 1 goes to 3. So we have 1 7 3. Now 3, we 5 fixes 3, 6 4 8 fixes 3, but 1 2 3 7 sends 3 to 7. Then we are back at 7, and then 7 goes to 2 in 2 7. So we are at 2. Then again we are at 1 2 3. 2 goes to 3. and then 3 goes to 1. So we have a cycle which completes here. So we don't write 1 here, we just complete the cycle here. So 2 goes to 3, and then 3 goes to 1. So we have a complete cycle here. Now we have 1, 3, 2, 7. Now let's see where is 4 going. So in 5 fixes 4, 6, 4, 8 sends 4 to 8, but 8 is fixed here. Okay, so 8 is fixed here. That means 4 goes to 8. Then we check 8. Now 8 in 6, 4, 8. 8 goes to 6, and then in 4, 5, 6, 6 goes to 4. That means we have a complete cycle. Perfect. That we are remaining with only 5. Now let's start with 5. 5 is fixed in this over here in 5, but 5 in 4, 5, 6 goes to 6. So 5 goes to 6. Now 6 goes to 4, and then 4 goes to 5. So this is again a complete cycle. And this is the cycle notation of alpha beta. This is their multiplication. This is how we do composition. Perfect. The important thing to bear in mind when multiplying cycles is to keep moving from one cycle to the next, from right to left. Okay? To be sure you understand how to switch from one notation to the other and how to multiply permutations, we will do one more example. Okay? So let's say we have two permutations, alpha and beta. This is, let's say we have late. Alpha is 1, 2, 2, 1, 3, 3, 4, 5, 5, 4, and beta is 1, 5, 2, 4, 3, 1, 4, 2, 5, 3. Okay. Now, then in cycle notation, alpha is nothing but 1, 2, complete cycle. 3 is fixed, then 4, 5. And beta is nothing but 1, 5, 3, complete cycle, and then 2, 4. Okay. Now, alpha beta is going to be, let's write them first like this. Okay. Then alpha beta, we see in 153, 2, 4 fix 1, 153, 1 goes to 5, but 5 goes to 4. So 1 goes to 4. And then 4 in 2, 4, 4 goes to 2. And in 1, 2, 2 goes to 1. So it is fixed. Right? And then we check 4. 4 is, so this is this becomes a complete cycle. Then we check 2. So 2 goes to 4, and then 4 goes to 5. So 2 goes to 5, and then 5 goes to 3, and 3 is fixed. So 5 goes to 3, and then 3, and now 3 is going to be fixed because 3 goes to 1, and then 1 goes to 2. So 3 goes to 2, and then it's a complete cycle. Okay. Now one can convert alpha beta back to array form without converting each cycle of alpha beta into array form by simply observing that 1, 4 means 1 goes to 4 and 4 goes to 1. So these are closed cycles. That's why I've been repeating that I've been repeatedly completing these cycles. And okay. So, one final remark about cycle notation is that mathematicians prefer not to write cycles that have only one entry. And in this case, it is understood that any missing element is mapped to itself. Now, with this convention, the permutation alpha can be written as here, permutation alpha can be written as 1, 2, 4, 5. Okay. I should say here can also be written as. Okay, perfect. Then, right. And using the same convention to say alpha is, which is here 1, 3, 2, 2, 3, 4, 4, 1, 5, 5 is in the cycle notation is just 1 goes to 3, 3 goes to 4, and 4 goes to 1. So it's a complete cycle. And then 2 is fixed, 5 is fixed, and that's it. Okay, this is how we can say. And now, what if you have all of those fixed? So let's say beta, which is like this, or let's call it epsilon. And so the identity, this is the identity permutation, and it consists of cycles with one entry. So we cannot emit all of these. In this case, one usually writes just one cycle. And for example, we just write epsilon is 1 or any number from 1 to 5. Okay, perfect. This was the cycle notation. We will pause our lecture here, and then we will define some other things in the next part. Thank you so much.